This is Joe. Joe's job is making sure the city's traffic signal controllers work, even in the worst possible weather. I wonder if Joe likes his new job as much as his old desk job.
Under normal conditions, traffic signal control equipment works as expected. Drivers navigate easily through intersections, and traffic flows smoothly. It's those unusual conditions that create havoc on the streets. You've likely been caught there yourself.
As a traffic systems professional, you can help eliminate the frustration caused by damaged traffic control equipment. In this video, we describe transient events that can affect the operation of traffic control equipment. We recommend devices to protect the controllers from these events and describe the differences in the devices. We'll show you where to place and how to install the devices in the controller cabinet. We also discuss grounding and bonding, as well as shielding practices and maintenance procedures.
The user's manual that accompanies this presentation contains charts, schematics, and additional details. From time to time, we'll refer you to the manual for more specific information. We recommend that you study the manual and keep it handy on the job for quick reference. Background information, design assistance, and performance specifications are available in the National Cooperative Highway Research Program, that's NCHRP Report 317, titled Transient Protection, Grounding and Shielding of Electronic Traffic Control Equipment, available from the Transportation Research Board. Lightning is the most severe natural threat to traffic controllers. The southeastern states and an area east of the Rockies experience the highest number of thunderstorm days per year. When lightning strikes a power system, it creates a power surge in the distribution lines that travels into traffic control equipment. But even during normal operation of a power system, power surges and switching transients can upset controller operations. Broadcast systems and other radio transmitters can also interfere with traffic controllers. A threat commonly experienced in the cold, dry regions is electrostatic discharge that results from component contact by maintenance personnel. All of these electromagnetic threats can enter the controllers along several paths. The most common path is the power line, followed by communication cables. Other paths are support cables, pole grounds, vehicle detector loops, signal leads, and any other cables entering the cabinet, like a pedestrian push button. Openings in the controller cabinet, like door seams and vents, can also provide a path for electromagnetic energy to enter the cabinet. When a threat enters the cabinet, it can upset circuits or destroy components. This illustration shows that the transients produced by these threats can easily exceed the tolerance levels of circuit components.
To protect controller equipment from these transients, you establish barriers in strategic locations. Common barriers are current limiters, voltage limiters, and electromagnetic or radio frequency shields.
Current limiters consist of fuses, resistors, and inductors. Voltage limiters are spark gaps, metal oxide varistors, and diodes. Electromagnetic shields are metal enclosures around the circuit to be protected. Filters can be both a current limiter and a voltage limiter. These barriers can be used individually or in combinations, but for any of these barriers to work, they must be properly grounded and bonded.
The most commonly used protector is the lightning arrestor. There are several types of arrestors: spark gaps, metal oxide varistors, and diodes. Carbon blocks and neon balls may even be found in older equipment. However, their slow response time makes them useless for protecting modern solid-state electronics.
Traditionally, spark gaps have been the most widely used type of arrestor. The two types are air gaps and gas tubes. Gas tubes are encapsulated electrodes filled with trace amounts of radioactive gases. The ones preferred for traffic controllers are gas-filled because of their predictable firing point. 2-electrode and 3-electrode versions are available. 2-electrode spark gaps can be used on single-ended communication lines or pedestrian push buttons. 3-electrode spark gaps can be used on balanced data lines. Gas tube arresters have 2 outstanding features. They can handle high-energy surges, and the 3-electrode types protect conductor pairs simultaneously. On the downside, the delayed firing time can let damaging energy reach susceptible components, and they are not self-extinguishing on DC-powered circuits. They can cause significant AC line distortion with loss of signal timing if the AC line frequency is used for signal timing. Spark gaps can also stay on long after the transient has ended, blowing fuses and breakers. Metal oxide varistors, or MOVs, are growing in popularity as transient limiters. MOVs have extremely fast response times. They can clip even the fastest transients. MOVs can limit transients with both positive and negative polarities. They occupy very little space and are inexpensive. But MOVs are limited in the amount of energy they can handle compared to spark gaps. Also, the high capacitance of MOVs can distort signals on data and inductive loop vehicle detector lines. Other devices are also used as transient protectors. By themselves, silicon avalanche suppressors and Zener diodes offer fast response time, but only unipolar protection. Packages are available that incorporate silicon avalanche suppressors and Zener diodes to offer bipolar protection. Silicon avalanche suppressors are often used after high-energy MOVs and spark gaps to clip the fast-rising leading edges of transients. As a transient suppressor, the common neon indicator light has an excessive turn-on time, so it's not recommended as a lightning protection device. Fuses and circuit breakers by themselves are not effective transient suppressors, but they're often used to limit the current flow, which follows the firing of other arresters. Low-pass filters can be used to limit high-frequency transient energy into susceptible circuits, too, and they also keep radio frequency energy out.
Though certain kinds of circuits can be protected by individual suppressors, experts agree that the best protection against transients and radio frequency energy is a combination of one or more suppressors and a radio frequency filter in proper order.
This schematic shows the proper ordering of a gas tube arrestor, low-pass filter, and metal oxide varistors for maximum AC line protection. A high-energy MOV is used to absorb the bulk of a high-energy transient and is placed closest to the cabinet entry point of the penetrating cables. The fast-acting MOV is located on the circuit side of the protector to prevent the leading edge of the transient from destroying the circuit. The filter must be located between the 2 suppressors to provide the delay necessary for the high-energy MOV to fire before the low-energy MOV fires. The spark gap is placed between the neutral wire and ground since timing will not be affected. The filter eliminates low-level interference that isn't high enough in amplitude to operate the transient suppressors. An integrated package is the ideal, but you can achieve the same result with discrete elements. Economy and space restraints will determine the appropriate configuration. When properly installed, either the integrated package or discrete components assures a viable protector. There are several commercially available integrated package suppressors for use in AC power, telephone, and other communications inputs. Make sure you use the appropriate suppressor for the input you want to protect to avoid signal distortion and circuit upset. When you select an integrated package, you need to be sure that it's tested to accepted lightning test specifications like IEEE Standard 587-1980. NCHRP Report 317 recommends test levels, wave shapes, number of pulses, and other test conditions for controller assemblies. If you specify suppressors that meet UL 1449, Be aware that the lightning test conditions specified in UL 1449 are not as severe as the specs in NCHRP 317. And be sure to get certified test data and circuit schematics so you know what you're buying. It will also help other maintenance and repair personnel. The guidelines in the user's manual can help you select the combination that's best for your particular situation.
Proper installation of an arrestor is essential no matter which arrestor you choose. Optimum placement depends on the location of the control equipment within the cabinet. We'll start with a model configuration, but remember, in all instances, the protector must be placed where it will limit the voltage difference across susceptible components to safe values. The best possible cabinet would look like this. All external cables are brought in through a penetration box. The lightning protectors are mounted inside this box. The protectors are well bonded to the penetration box, and the input and output conductors are isolated from each other. By putting the protector in a penetration box, we keep the lightning away from susceptible components. This design also makes a good path to earth for the lightning current. Although future cabinet design is moving in this direction, we still must protect existing equipment. Here's an example of a fairly well-designed controller cabinet. Power and communications cables enter through the bottom of the cabinet. Power cables run up to circuit breakers. We have EDCO suppressors, followed by an RFI filter in parallel with the EDCO suppressor. The ground rod is a 5/8" galvanized rod with a copper bolted connection. Solid number 6 runs over to the chassis. The neutral and the ground are connected because code permits it. We have metal oxide varistors on the various load lines. And over in this corner, finally, we have 3-terminal spark gaps on the vehicle loop detectors and communications lines. You can't fully protect traffic controllers from electromagnetic threats without proper shielding, grounding, bonding, and maintenance. Here are the techniques and practices that assure maximum protection.
Without grounding, protectors don't work. Both the National Electrical Code and local codes specify grounding practices that meet personnel safety requirements, but these practices are not adequate for proper protector performance. Lightning grounds require a much lower impedance path to earth than safety grounds. They need to be short, wide metal paths to accommodate lightning pulses. That's why a metal cabinet is better than the wires specified by codes. In fact, you need to make sure that the electrical ground wire, or green wire with AC service, and the ground rod are interconnected through the controller cabinet. Ground rods provide the necessary path to earth for lightning and fault currents. The path from the ground rod to the cabinet must have low impedance, so make the connection between the ground rod and the cabinet with the shortest possible lengths of wire. We recommend a copper-clad bare wire, number 6 gauge or heavier. Standard 8 to 10 foot lengths of copper-clad steel or galvanized steel rods should be adequate for the earth ground in most cases. For large installations, it may be necessary to use larger rods and multiple rods to form a grid. After installation, follow the procedures in NCHRP Report number 317 to measure its resistance to earth. When direct contact with earth is impossible, like at intersections on a bridge, you can ground to water pipe, reinforcing steel, or support pilings. Pole grounds are installed by the power company. They connect the distribution ground cable to earth. Since the distribution ground cable is usually the highest conductor on the power line, it's frequently struck by lightning, so you don't want to attach support or messenger cables directed to the pole grounds. Support messenger cables on separate poles. Place the support poles at least 6 feet away from the power pole. Install separate grounds for each support pole. Ground the messenger wires to the support pole ground rods. If you don't have 6 feet of space, interconnect the support pole rod to the power pole ground with nothing smaller than a buried bare number 6 copper cable. Ultimately, good grounding depends on good bonds.
Bonding makes those low impedance connections between conductors. Because of their permanent nature, exothermic welds are preferred over clamps in making the connection of the ground rod wire to the ground rod. Here's a demonstration of exothermic welding. First, carefully read the manufacturer's instructions and safety precautions. Next, clean the top of the rod and the end of the wire. Then, slide the exothermic weld crucible over the end of the rod and slide the wire and related parts in place. Drop the disc in, pour the weld material in, place the cap on the crucible, and then pour the igniting material onto the cap. Ignite the weld material using a flint striker and you are done. You can break the crucible to check the weld after about 30 seconds, but be careful, it's very hot.
For most connections, welding is impractical. When you can't weld, use bolts or screws. Never use solder by itself in lightning or fault discharge paths. And don't use rivets for electrical bonding. No matter which method you use, be sure to clean the contacting surface as well. When you have to bond to dissimilar metals, use approved bimetallic fasteners or treat the surfaces as described in the manual.
Bonds are an important part of shielding too. Shields protect against radiated energy that can upset controllers. The perfect shield is a metal box with no openings, but that's impractical. The next best shield is a box with well-bonded seams and properly treated openings. Cabinet seams should be welded, and openings should be covered with wire screen or a metal gasket. Unfortunately, that's costly. The good news is it's not necessary in most cases. When is it necessary? If the controller is near an air traffic control radar, a broadcast tower, or a military installation, you'll want that maximum protection because electromagnetic interference is more of a threat. Cable shielding is another important part of lightning protection. If you're puzzled about the proper grounding of cable shields, you're not alone. Many professionals are confused because cable shields provide an electromagnetic barrier while at the same time they serve as pickup paths for lightning. There is no perfect solution.
For maximum protection against lightning and other electromagnetic threats, ground the cable shield to the cabinets on both ends. We recommend using connectors that completely enclose the cable inner conductor. This is peripheral bonding. Grounding at both ends creates ground loops and can cause problems in some circuits like inductive loop detector inputs. If you can't ground one end of a cable shield, connect a suppressor between shield and ground to prevent arcing to the inner conductor.
Whenever possible, eliminate all openings in the cable shield. If you bond the cable shield peripherally at both ends, you provide a closed electromagnetic barrier. When you can't avoid pigtails, be sure to keep them as short as possible. To combat ground loop currents, use the rejection techniques described in the user's manual.
Once the traffic controller is fully protected, you can save hours of repair work and keep traffic moving if you follow up with periodic inspection. Check each box you're assigned during repair calls and routinely at least once a year. Look for several key indicators that fall into two categories. The first category is evidence of lightning. Look for cracked or burned arresters, circuits, and components. Check for carbon tracks, melt points, and discoloration on wires and terminals. Blown fuses and tripped breakers are also signs of lightning damage. Normal wear and tear is the second category. Look for corrosion, particularly in bonds at cabinet connections, ground wires, and arrestor leads. Use your ohmmeter to check for electrical continuity across corroded joints. Corrosion will be obvious, but you may have to search harder for broken wires, especially in arrestor leads. Make sure that all ground wires are unbroken and connected. Temperature changes loosen wires, so test for loose bonds, particularly where bolts or screws are used. Pay attention to bonds and grounding conductors. If the ground rod connection is bolted, be sure to check it for corrosion and looseness. When your maintenance check is complete, replace the damaged components and clean and tighten the connections.
By the way, if you're working on a controller in cold, dry weather, you'll want to avoid static discharge. Did you know that modern solid-state electronics can be damaged by an electrostatic discharge even if the electronics aren't operating?
It's true. So before touching any solid-state circuitry or printed circuit boards, you need to touch or connect to a solidly grounded object, like the equipment cabinet. Same for working on a bench in the repair shop. Ground your tools and put conductive pads on the work surface. Ground your rolling chairs and carts, or roll them on a conductive pad that's tied to a ground. We recommend wearing a conductive wrist strap while you work.
You've just seen the basic guidelines of good traffic controller protection, but certain situations may require special attention. The user's manual explains these procedures in greater detail, or you may contact controller manufacturers or arrestor manufacturers for more specific information. You can also consult NCHRP Report 317 for background information, assistance in design, and formulation of performance specifications. To get a copy, call the Transportation Research Board Publications Office at area code 202-334-3218. Make your job easier. Specify and purchase transient protected signal controllers in the first place. And if you maintain your protected traffic controllers properly, you'll keep traffic moving everywhere.